So I would like to start the presentation on Lupus, a monitoring system for accelerating MLOps. Here are the intended audiences for this presentation. First of all, those who are currently managing and operating machine learning products. In this presentation, I will discuss the monitoring which is essential to operate machine learning products but rather cumbersome and difficult to focus on. I would be happy to consider with you ways to ML production more stable, focusing on improvement of monitoring. Next, those who are members of organizations developing services using ML that are expected to grow further in the future. Line's machine learning department has been in existence for many years, counting from its predecessor organization days, and currently we are operating a huge number of ML products, and we are facing the issue of bloating the monitoring costs. In this presentation, we will share some of the troubles that we have experienced related to lack of monitoring and solutions to address them. Last but not least, those who are interested in MLOps. MLOps is a methodology for operating an ML product that has been attracting attention in recent years. In this presentation, I will discuss what MLOps is, and I will also introduce the MLOps that the machine learning department is implementing. So please enjoy the presentation through the end. This is the agenda for the presentation. First, I will talk about what is monitoring in MLOps. Next, I would like to introduce the overall picture of MLOps in Line's machine learning department. After that, I'd like to talk about the monitoring challenges we are facing. And then I will introduce Lupus, the monitoring platform we are developing to address these issues. Before the presentation, I'd like to introduce myself. My name is Junki Ishikawa, and I am a member of the machine learning development team in the machine learning department. I joined the company as a new graduate in April of last year. My work includes recommending stamps, developing in-house libraries, and I also develop internal tools including Lupus. In my private life, I live with my 2 Java sparrows. Before I start with the main content, I'd like to explain what is MLOps and what is monitoring in MLOps. MLOps is a word that is fusion of ML and DevOps. It means DevOps in ML product development. Recently, many services based on ML technology have been developed. However, it has become clear that there are some requirements that cannot be covered by the traditional DevOps framework. As a result, there is a lot of discussions ongoing in many places about MLOps. So what are the peculiarities of MLOps from a DevOps perspective? First, in addition to usual DevOps, MLOps includes the design and the validation of ML models. Here, we design a machine learning model, evaluate its performance through experiments, and develop logics to meet requirements. There are also other requirements beyond model development, such as how to collect data. This part is generally highly specialized, and then in order to provide services, it requires us to collaborate with the ML engineers, data scientists, annotators, which is a great difference compared to usual DevOps. Also, the DevOps cycle includes some unique requirements. For example, how to secure and allocate resources to deploy the model as a service, and where to let the model get trained, how to release and deploy. And in production, the model retraining is prompted when model's accuracy becomes degraded. Monitoring is the key to operate this lifecycle. In MLOps, there are uncertain factors that are not managed by code such as data and models. These factors can also change over time. For this reason, monitoring in MLOps has requirements that are not found in regular DevOps. So what kind of metrics do we need to collect in MLOps? To think about this, let's first consider the usual monitoring in DevOps. In a regular DevOps, you would collect metrics such as usage rate of resources, including CPU, memory, disk I/O traffic, as well as the system heartbeat. It is also recommended to monitor business KPIs and DevOps KPIs. In DevOps, the monitoring is focused on the system's operational information. In addition to this, MLOps requires monitoring of data and machine learning models. First, you need to monitor the data that are handled. For example, there is no guarantee that the distribution of the input data will not change over time. Therefore, the distribution may deviate significantly from the distribution assumed at the time of training, and the quality of the service may deteriorate. This phenomenon is called data drift. Missing data may be considered as a special case of data drift. Also, the relationship between the target variable to be predicted and its input data may change. This phenomenon is called concept drift. Therefore, in MLOps, it is desirable to monitor the volumes of statistics of the data handled on a daily basis. We also need to monitor what kind of output machine learning model is making. For example, it is a common practice to the prediction accuracy of the model, and if the accuracy deteriorates beyond a certain level, we can prompt the model to be retrained. In addition, there are task-specific metrics as well. For example, the diversity of recommendation system is said to have a significant impact on long-term service improvement. And in recent years, fairness, which indicates where the model's predictions are not discriminatory, has also become an important metric. We can think of some other differences too. For example, in DevOps, it is possible to collect metrics in an automated manner to a certain extent by using the cloud. On the other hand, metrics in MLOps are highly dependent on the environment surrounding the service, so it is often difficult to collect them automatically. There is also a slight difference in terms of the frequency of collection. For monitoring compute resources in DevOps, metrics are collected at a high frequency. On the other hand, for MLOps-specific data and models, the changes are often more gradual. These metrics often require a lot of data and are expensive to aggregate as well. Therefore, they are often collected every few hours or every few days. There is also a difference regarding alerts. Metrics in MLOps are often periodic or trending, so simple threshold-based alerts often do not meet the requirements. In light of these factors, it turns out that developing a sufficient monitoring environment for MLOps is more costly than you might think. And the more products you operate, the more expensive it becomes. Line's machine learning department operates a large number of ML products. In this presentation, we will introduce our approach to provide a sufficient monitoring environment for each product. I would like to start with the explanation of the scale of the approach and the challenges by describing the overall picture of MLOps in Line's machine learning department. The machine learning department is a cross-sectional organization, and we provide ML products to various services in collaboration with each business unit. For example, we are involved in estimating the attributes of Line users, recommending books, optimizing advertisements, etc. The machine learning department is currently working with over 20 organizations. The total number of ML products we provide with them is over 100. And in operating them, we deal with a large number of data sources. For example, there are over 500 Hive tables provided by external organizations. Referring to data sources that are not under our control can easily become a starting point of failure. If you imagine an environment with a large number of such data sources, you can understand the scale and complexity of the products that machine learning department operates every day. I would like to introduce some more data to give you a sense of scale. The Line app has a frame called Smart Channel that displays content which is appropriate for the user. You may have seen stamps and news recommendations displayed at the top of the talk list. There are many logics behind the smart channels to display contents, and contents that are suitable for users are selected by bandit from these logics. The ML department also provides a lot of these background logics. The graph on the right shows how the number of logics handled by the smart channel changed over time. the number has increased tenfold in about 2 years. The number of products that the ML department has for the Smart Channel has also increased proportionally. This is just one example, but you can see that the number of ML products at the ML department is increasing at such a rate. In order to develop products at such a speed, it is important to develop a right environment and right tools. The ML department has developed a number of infrastructure environments and in-house tools for rapid development and stable operation. Please let me introduce them briefly. First, we use Kubernetes and Hadoop as our primary computational environment. Line is running a huge Hadoop cluster called IU, and data from each service is dumped into the IU on a daily basis. Data analysis and experimentation are done using our in-house Jupyter server. Batch jobs utilize a variety of workflow engines, and release management with the CI/CD tool is standard. Next, let's take a look at some of our in-house tools. The first one is the feature vector. Since feature volume such as user behavior logs and item meta information can be used in many products, we are trying to aggregate them so that they can be used efficiently. We also develop many in-house libraries. These allow us to handle large and complex data of line in a stable manner. In addition to the libraries, we also develop auxiliary tools to facilitate actions. For example, we develop A/B test management systems and web apps that generate recommendation demos. These tools cover these areas in the product development done by the ML department. You can see that they support each step of the ML product lifecycle. However, until now, there have been no tools to streamline the monitoring. To be precise, we have been using Prometheus and other tools to monitor the computational environment, but the monitoring of ML was built by each project. Therefore, it was not uncommon for us to notice a failure based on an alert. With such operations and rapid increase in the number of products, the sense of issue about monitoring gradually increased. So far, I have talked about the overview of MLOps that is done by the machine learning department, which has a large number of products. I also said that the monitoring is operated independently by each project, which we feel is a significant issue. Maybe some of you who are feeling the same way about this issue too. In this section, we will discuss in detail the challenges we faced in the machine learning department regarding monitoring and the actual failures that occurred. The first issue is the increase of monitoring cost. As I mentioned earlier, the ML department developed and operates more than 100 ML products, and the data sources used by these products are also diverse. So far, the ML department has developed in-house tools and have become able to develop ML products more quickly. However, the more products we operate, the more the cost of monitoring increased, and it's been happening. In addition, monitoring and alerting mechanisms are often independently operated for each project. However, monitoring systems created independently for each project tend to be weak, covering only the minimum or only alerting, but not storing metrics. There is also a high degree of dependency on project and project members. If there is not enough monitoring in this way, or the coverage is not sufficient, it can eventually lead to failure. There are many factors that can cause failures in ML products, for example, missing data, changes in distribution, model updates, etc. However, it is very difficult for people to check anomalies one by one every day when operating many products. It is also very difficult to set up a powerful monitoring environment from scratch. In this section, I will introduce the actual monitoring-related problems and failures that occurred in the ML department. This first example is about missing data. A typical batch job at an ML department is to read the most updated data from tables that are provided by external organizations every day. The model is then trained and predicted based on this, and then prediction results are shared with the external organizations. In this case, if any of the provided tables fails or is delayed, part of the data may be lost. However, if the input-output of the ML product is not monitored properly, you may not notice anomalies in the prediction results even if they are occurring. This can sometimes lead to inappropriate or empty predictions, which can lead to failures, and it has been happening sometimes. Next is about updating the model. In one of the products, training and the task of estimating user attributes is done every day. At some point, in order to improve the prediction accuracy, we did a release that significantly changed the structure of the model. But at this time, a significant difference in the distribution of predictions between the new and the old models was overlooked. Even if the overall accuracy becomes better, if the distribution changes significantly, the individual user's attributes will suddenly change dramatically. When this happens, it has a significant impact on the services in terms of user experience, as there were significant changes in provided contents. In addition to stabilized predictions, post-processing was done in such a way as to take a majority vote over the predictions of the past models. So there was a delay of about 2 weeks before this problem occurred and revealed. This meant that it took a long time to identify the cause, and it was very costly to fix it. We believe that if we had properly monitored the daily predictions of the model and the final prediction results, we could have dealt with the problem much earlier. The last example is about the project which created the original monitoring environment. This project used the Jupyter Notebook to check and visualize some metrics. This approach is convenient because it allows for flexibility, but it also posed some problems. For example, the metrics collected were only what were needed at that time, and the conditions for alerts were limited to simple ones. Also, code reviews were not often done, so there was a lack of fundamental reliability. Through these experiences, we thought about what we need to do to improve the monitoring environment. First, regarding the collection of metrics. When doing monitoring, engineers struggle to identify what to aggregate and where to store the metrics. In addition, it is not often the case that an engineer's main area of interest is the monitoring. So we needed a system that would make the collection of metrics as efficient as possible. Specifically, we thought we needed a toolset for calculating metrics and storage for them. Metrics collection in MLOps involves aggregation of statistical volume of data and evaluation metrics of the model. This can often be a tedious process and cumbersome. So by providing tools to aggregate various metrics, we can reduce the cost of aggregation. We also want to lower the barrier to implementing monitoring as much as possible by providing a reliable and easily accessible metrics store.
Since it is difficult for humans to go through a large number of metrics, we need a mechanism to detect anomalies and notify to the users. As I mentioned in the first half, anomalies in MLOps metrics often have a trend or periodicity. So, you need a flexible anomaly detector and an alert system to notify you of detected anomalies. Finally, we thought that we needed a visualization system that would allow us to easily view the collected metrics. In addition to detecting anomalies with alerts, visualizing how the data and models are changing can help us understand trends and get new ideas of improvements. At this time, the metrics are not only built by engineers but also by PMs and business unit staff. Therefore, we thought that an application that can be easily operated is necessary. Lupus, which I am going to introduce, was created with such a development goal in mind. So, without further ado, I'd like to introduce a monitoring system we are developing. That's Lupus. Lupus is a common monitoring platform for MLOps that we are currently developing to solve the monitoring issues in the MLOps room that we have discussed so far. Its name is Wolf Constellation in English. Lupus has 3 concepts that reduce the workload involved in monitoring. First, engineers can easily collect metrics. Second, operators can easily detect anomalies in the product. Finally, all project members can easily visualize metrics and anomalies. Based on these concepts, Lupus consists of 3 components: server, the library, and SPA. The server provides APIs for recording metrics, anomaly detection, and alerting services, as well as authentication and meta-information management. The library is a Python library that provides a set of tools for general-purpose metrics collection and an API client for the server. SPA is a browser application that allows for exploratory visualization of recorded metrics and alert information. This is the entire ecosystem of Lupus. The library is used where metrics collection occurs, such as in batch jobs. The library is not required, and Lupus can be used from any environment where REST API is available. The collected metrics can also be accessed through SPA. The Lupus server is a point of entry for all requests and performs proper authentication. For example, when metrics are sent from batch job, the decision to accept the metrics is made through token-based authentication. On the other hand, access from browser is tied to a line employee's account that identifies each individual, and users can only access the information for which they are authorized. Metrics fetching and anomaly detection execution are processed asynchronously and in parallel using combination of job queues and worker processes. The specific execution of the process is done using algo flow. The Lupus worker processes are only responsible for managing workflow execution and recording metadata. By separating the mechanism for parallel job execution from the highly specialized and demanding service logic, such as anomaly detection, we can facilitate the development and management. The storage of metrics and anomaly information, we use Elasticsearch and Hive. Elasticsearch for visualization and search, and Hive for long-term storage. I will now introduce the functions provided by Lupus and their use cases in 3 categories of metrics: collection, anomaly detection, and visualization. Let's start with the collection of metrics. As mentioned in the first half, MLOps requires monitoring of data and models. In the data drift, where the input data changes, and in the concept drift, where the objective variable changes, we can monitor the statistics to a certain level. It is also necessary to monitor the performance of the model to deal with changes such as model degradation and retraining. In addition to collecting statistics or predictions, performance evaluation using two values and metrics during the model trainings are also useful. Let's look at some specific examples. The Lupus library provides support for computing statistics. Let's see some examples. Let's say you have a large amount of data and you're using PySpark for large volume of distributed processing. It may be a common case that you want to collect various statistics, like the one on the right from each column in groups like region. However, the actual writing of these statistics can be quite complicated than expected. I tried to write the code myself, but it was still very long and tedious. And also, I had to think about how to process by column type. For instance, from the array column to extract the top K information, or if you want to extract the statistics for each category in a category column, the code will be long. And I don't think many reviewers would want to read such a document. I don't want to read it. The Lupus library makes it easy to write this kind of aggregation process. All you have to do is to write the columns to be grouped and the metrics you want to aggregate for each column in a declarative manner, and the metrics will be calculated. This alone should lower the hurdle to implement statistics monitoring. The library also supports evaluation metric calculation. For instance, in a multi-class classification problem, you can calculate precision recall F1 score by passing pairs of prediction data, and collect answer data as shown in the table on the left. It can aggregate other distribution information such as level counts. It also supports the calculation of variation indicator for recommendation questions. In particular, it is easy to specify the metric calculation for top K. There are other advantages to supporting the calculation of variation indicators. It increases the reliability when comparing indicators between projects. Although it is often overlooked, metric calculations can vary in detail depending on their implementation. In particular, since the definition of some metrics such as NDCG are different from each other, the implementation for calculating metrics must also be aligned if you want to make comparisons with logic. The more members use the metrics calculations provided by Lupus, the more credible the result will be when compared to previous results. In addition, there is a function to retrieve the metrics recorded in MLflow. In the ML room, we use MLflow for learning management. Various metrics recorded in MLflow can be fed into Lupus for common reference along with other metrics. In the next section, I will show you how to collect metrics using Lupus. This is a flow of metrics collection. First, the user calculates the metrics he wants to collect. This step can be done efficiently by using Lupus library as described earlier. Of course, you can also calculate your own metrics. The next step is to send the collected metrics to the Lupus server. The library has a client class for the API, so it is easy to send them. This is all the user has to do, and it can be as little as 10 lines of code. Here's the other side of the story after you send it. When the Lupus server receives metrics, it places the data into S3 compatible object storage at once. After that, the job to record the metrics is registered to the job queue. The worker process retrieves the job from the job queue and execute it in Argo workflow. After retrieving metrics from storage, the workflow validates the data. After confirming that the data is in a normal format, it writes the metrics information to Hive and Elasticsearch. This is a flow until the metrics collected by the user are persisted. Next, I will discuss anomaly detection for metrics. As I have mentioned several times, anomaly in MLOps have a hypertext component. The basic alerting system, as you can see on the left, is to issue an alert when a threshold is exceeded or when there is a significant change from the most recent value. In MLOps, on the other hand, metrics are often cyclical or trending. Therefore, it is desirable to be able to detect significant deviations from periodic changes or changes in trend as shown on the right. To approach this problem, Lupus implements an advanced anomaly detector that utilizes machine learning. Lupus currently implements 4 types of anomaly detection logics. The basic anomaly detection is based on threshold or window based on the most recent value as a baseline. In addition to the above, prophet-based anomaly detection is implemented as an advanced method that utilizes time series prediction. It uses prophet to make time series predictions based on past data and judges whether there is an anomaly or not based on the confidence interval. In addition, anomaly detection is implemented using a library released by Twitter as OSS. Since we paired all these by ourselves, we will continue to add logic based on our own requirements. I'd like to introduce the flow of performing anomaly detection. Anomaly detection is triggered from the user's request. The user specifies the range of metrics to be detected and the parameters of the anomaly detector. The Lupus library implements an interface and client for this purpose, though the user can make the request intuitively. Requests are registered in the job queue and are processed sequentially. The anomaly detection workflow first reads the metrics specified by the user from Hive, and then performs anomaly detection for each metric series. If the number of series to be handled is large, relatively heavy processing such as time series forecasting for each series will take a very long time to calculate. Therefore, Kubernetes is used to perform distributed processing as needed. The result of the anomaly detection are saved in Hive or Elasticsearch and then notified to the user. Finally, I will explain the visualization part using Lupus SPA. The Lupus SPA is a single-page application to visualize collected metrics and alerts. The information to be displayed is stored in Elasticsearch and retrieved via the Lupus server. The Lupus server has user authentication and controls who can see which metrics. So only users with proper permissions can see the information. Through the Lupus SPA, users can visualize metrics, explore charts, and use customizable dashboards. You might think there are so many other tools as such. In fact, Elasticsearch has a visualization tool called Kibana, and we look at data in Kibana when we develop Lupus. So, why did we build it from scratch ourselves? There are several reasons for this. First, we want to provide a simple UI that is optimized for our use. There are a lot of great OSS out there, but they're pretty generic. So, for example, you may need a query language with high learning cost. Lupus has a common schema, and we wanted to create a simple UI that focuses on use case. There are also requirements that are specific to Lupus. For instance, we want to display anomaly detection information and narrow down metrics. In addition, we need a complex authentication mechanism to maintain high level of security. So we thought it would be best to build it ourselves. From here, I will introduce each screen of the Lupus SPA with sample data. From the left-hand side, you can move to the dashboard. From the right side, you can jump to the list of data sources and explore the various charts. In Lupus, metrics are divided into units called data sources, and users can create data sources and inject metrics into them. Next is the chart exploration screen. Here you can explore the chart of metrics collected so far. This sample screen shows the information collected by the data source called Job Service 1 Recommend. The text is a bit small, but for instance, the chart on the top left shows the NDCG values for this recommendation for this service. In addition, recall and entropy, which is one of the indicators of recommendation diversity, are also collected, and this screen shows all indicators at once. Click a chart, you can move to the chart details screen. Here, I can narrow down the range of metrics to be displayed. The NDCG chart for each region is displayed on the screen. When an anomaly is detected, the point where the anomaly is found will be annotated like this. Each series of metrics has grouping information that can be specified by user, and you can filter them in the UI freely to see only the information you need. In addition, by clicking one of the metrics series, you can view detailed outlier information. For instance, depending on the logic of anomaly detection, there may be confidence intervals or expected series, so you can visually check such meta information. This is a dashboard screen. Users can select a chart to create a dashboard and quickly access the information they need. In this screen, you can see the information related to the Service 1, which is consolidated. This concludes our introduction of the feature of Lupus. Finally, although Lupus is still in the development stage, I'd like to introduce some of the improvements that have been made by implementing Lupus. First, Lupus has made it easier to collect metrics on a daily basis. Although, through Lupus, we were able to notice the triggers of failure that we were not aware of before. By collecting and visualizing metrics on a daily basis, I was able to notice changes in accuracy that I had not known before. This motivated me to improve the product. The monthly notebook, which was not reviewed, are now replaced by Lupus batch job, which will increase the reliability by including code reviews. In addition, by using Lupus to collect metrics on a daily basis instead of taking a long time to do ad hoc aggregation when needed, we are able to collect metrics with a fine frequency and see the latest information immediately. It has also made it easier to share the information with members through Web UI. Here is a summary of this presentation. In the beginning, I talked about modeling of MLOps and explained that there are requirements that are not found in general DevOps. Next, I introduced the challenges that the machine learning office at Line is facing. There are so many different products, and it is difficult to maintain a solid modeling environment for each one of them. And lastly, I introduced Lupus, which is being developed to solve this problem, aiming to create an environment where people in various positions, such as engineers, operators, and PMs, can monitor without difficulty. Lupus is still in the development stage, but we were able to show the great impact it has been, even in experimental implementation. I hope that the experiences and solutions will give you some hints to improve your modeling environment. This is a list of books and websites that I referenced in the development of Lupus in this presentation. This is the end of my presentation. Thank you very much.